So this is meant to be a combination, a talk that sort of combines distributed computing and game theory. And it really does have to do with decentralization, which is what this is about, I guess, despite the subtitle. So let me explain the pieces. I don't have a good sense of your background, so this is, again, where it's useful for me to encourage you to ask questions, because if you're all nodding and smiling and happy, I'm going to assume you know this stuff. But if that's not the case, ask. So historically, and when I say historically, I'm thinking about 20 years ago or more, there were two views of the world, one in distributed computing and one in game theory. So in distributed computing and game theory, and cryptography, the picture was we have good guys and bad guys. The good guys do what they're supposed to do. You give them a protocol, they run the protocol. Bad guys do everything they can to subvert it. And I think historically the motivation was that the system designer writes a protocol, but some computers might be flaky and not do what they're supposed to do. Those are the bad guys. And because you don't want to, you want to look at the worst case, say, okay, if they're going to be bad, they can be arbitrarily bad, although there were constraints put on that. So a totally different view of the world is what you get in game theory. Game theory says, no good guys, no bad guys. We just have rational agents. This is traditional game theory. They're going to maximize their utility. They'll do what they're supposed to do if it's rational, if it's best for them to do what they're supposed to do. If not, they'll try to subvert the protocol. All bets are off. But they're rational. They're not going to do it unless they can get some advantage out of it. Does that make sense? So there are these two pictures. Sort of weird for me to have audience over here as well, but that's okay. Both of these make sense, but I claimed, in fact, in a setting like blockchain, they absolutely make sense. It makes sense to combine them. You certainly have faults in the blockchain setting. It's a distributed system. Computers might crash or fail other ways. And you certainly have rational agents who might want to subvert the system and make all sorts of money. Right? So that's the picture we're looking at here. So there are three threads to the talk. The first thread, I think, comes from the distributed computing community. And we care about fault tolerance. So let me ask, when I say Byzantine agreement, how many people have not heard of Byzantine agreement? Raise your hand if you have not heard of it. I don't see one hand. Well, a few hands. I'll talk about it quickly. I mean, don't feel bad. It's okay. It wasn't a requirement that you know Byzantine agreement. But it's good that so many people of you have heard of it. It's a paradigmatic problem in distributed computing. Goes back to Lamport, Peace, and Shostak in the mid-'80s, I want to say, maybe early '80s. So at this point, it's over 40 years old. And the story, which is meant to motivate it, is there are N soldiers. Up to T of them might be faulty. So T is a parameter. So there might be up to T bad guys. And everybody knows N and T. But remember, T is only an upper bound on the number of bad guys. There could be far fewer. So T is the amount of faults you're willing to tolerate. Now, each soldier starts with an initial preference to either attack or retreat. And we want an algorithm that guarantees that if all the non-faulty soldiers follow the algorithm, because all bets are off for the faulty ones, so if all the non-faulty ones follow the algorithm, then they're all going to do the same thing. Either they're all going to attack or they're all going to retreat, and they'll do it at the same time. So this is what's called simultaneous Byzantine agreement. And if all the soldiers are non-faulty and their initial preferences are identical, that's what they do. So if you all want to attack, then they should attack. Now that second assumption just prevents the trivial solution of everybody attacking no matter what. This just says, well, look, if everybody initially wanted to retreat and none of them were faulty, then they should retreat. So are we together? That's the problem. And Byzantine agreement has been the basis for all sorts of agreement algorithms. Not exactly the one used in blockchain, but certainly similar in spirit to the ones used in blockchain. So here are the kinds of results you get. And, you know, this is an area that has been mined to death by the community, so lots and lots of results are known. But I'm stating these results here partly because I want to relate them to later results. So with Byzantine failures, and when I say Byzantine, I mean soldiers can lie and cheat and steal and be bad in arbitrary ways, then you can get agreement, but only if at most 1/3 of the soldiers are faulty. If, remember, T is the number of, upper bound the number of faulty guys, so 3T has to be less than N. Otherwise, you provably cannot get agreement. But if you only have crash failures, or crash failures say, look, at least if you're going to be faulty, you'll shut up and die. You won't say bad things. Then agreement is always possible, as long as, you know, for any N greater than T. Now with Byzantine failures in cryptography, that is, when I say cryptography, I mean messages can be signed using cryptographic techniques with unforgeable signatures, then agreement is always possible. So that 3T's less than N that I had at the beginning only applies if you don't have cryptography. With cryptography, you can get agreement if N is greater than T. Now here's something interesting. If you're going to agree at all, if you can agree, it'll take you T+1 rounds. Remember, T is an upper bound to the number of bad guys. This is true even if you don't have any failures, and even if you have only crash failures in the worst case. So you have to run for T+1 rounds because you're worried about things that might go wrong, it turns out. And this is a low, you know, a tight bound. You really need T+1 rounds. And if you're a game theorist, you can kind of think of Byzantine agreement as a game between two teams, the good guys and the bad guys, except you don't know who's on the team. You don't know who the good guys are and who the bad guys are. Okay, that's thread 1 was Byzantine agreement. Thread 2, sort of cryptography, multi-party computation. So multi-party computation goes back in computer science to the early 80s. Andrew Yao, who won a Turing Award, that's our Nobel Prize. Silvio Micali and Avi Vigdusson. Silvio and Avi both won Turing Awards. Oded won an Israel Prize. I mean, these are quite famous computer science folks. And the paradigmatic problem in multi-party computation is that each agent has some secret input, and you want to compute some function of those inputs, like the max. You know, if everybody's input is their salary, who has the highest salary? But you want to compute that answer without revealing any information besides the answer. So, in other words, if your secret input is your salary, and the function is to compute the highest salary, well, at the end of the day, you'll know what the highest salary is, but you won't know anybody's salary in particular besides your own, right? You won't know who has the highest salary. That's the idea. And the picture that they had quite explicitly in the papers was, imagine you had a trusted third party, a trusted mediator. And you could tell that trusted mediator, thank you. You could tell that trusted mediator your salary, and the trusted mediator would announce the highest salary, but wouldn't reveal anything else. So keep that trusted mediator in mind. We're coming back to him. And again, there are protocols for multi-party computation. And again, the model was there's good guys and bad guys. So you want to do this even if you have a bunch of faulty agents. And you can do it assuming that no more than a third or no more than a half of the agents are faulty, depending on your underlying assumptions. Okay, that was thread 2. Remember, thread 1 was Byzantine agreement. And thread 3 is mediators. So let me talk more about mediators. So imagine an auction where people don't want to bid publicly. So why not? Well, if you bid publicly, that reveals information. Imagine you're bidding on oil tracts. You're different oil companies, and you're bidding on, who has the rights to drill in various places. You don't want to reveal how much you're willing to bid, because that will tell other companies maybe information that your engineers have found, oh, this is a good area to drill in, right? So you want to be able to bid without revealing information. And one way to do this, sorry, let me go back. If we had a trusted third party, you'd be all set, right? Everybody could tell the trusted third party their bid, and the trusted third party would say, okay, you won, done, and not reveal anything else. Okay, so here's the part where I want to talk about centralization and decentralization. Think of using a trusted third party as a centralized protocol. And the question we're asking is, can we get rid of the trusted third party and just have the agents figure out the answer themselves, but get the same outcome as if they had a trusted third party? That's the decentralized version. And the answer is going to be yes, provided you have enough agents, but let's get there a little bit slower. So, all right, how many people here have heard of Nash equilibrium? I take it back, have not heard of Nash equilibrium. Raise your hands if you haven't. So I see a few hands. Let me explain. So Nash equilibrium is a concept, is a concept from game theory, and it applies to games. And it says, well, we have a Nash equilibrium if everybody's playing a strategy and no single person can gain by deviating. We're in equilibrium if nobody can gain by deviating. Nobody can gain by doing something other than what they're doing. Now, Nash equilibrium is not necessarily a good strategy. It's just a stable point. It's an equilibrium. You can't do no single person can do better by deviating. But it's perfectly consistent. So does that make sense? If it doesn't make sense, ask questions. Right? So again, this is going to be an important concept. So Nash equilibrium, nobody can gain by deviating. But it's perfectly consistent with Nash equilibrium to say, hey, you and I, we could do a whole lot better if we deviated. Perfectly okay. We could have a Nash equilibrium where if both of us deviate, we would do better. Okay, there's nothing inconsistent about that. So here's an example. So suppose you have n players. Think of n as 50 or 100, doesn't matter. They have to play either 0 or 1. If everybody plays 0, then everybody gets a payoff of 1. So if they all do the same thing and play 0, they get a payoff of 1. If exactly 2 players play 1 and all the rest play 0, those 2 players get a payoff of 2. The rest gets 0. And if it's not the case that everybody plays 0 or exactly 2 players play 1 and all the rest play 0, then everybody gets 0. Does the game make sense? Right? In this game, there's one Nash equilibrium where everybody plays 0. Everybody plays 0, so everybody gets a payoff of 1. And no agent can gain by deviating, because if that agent deviates and plays 1, then we're in the third case where everybody gets 0. But certainly 2 players can gain by deviating. If 2 players deviate and both play 1, they're in the second place and they get 2 rather than 1. So this is a case where we have a Nash equilibrium, but we don't have what we're going to call two resiliency. So in general, K resiliency says no group of K agents can gain by deviating. So why do we care about this? Well, certainly in blockchain and lots of applications, we can form coalitions. So Nash equilibrium just says no one person can gain by deviating. K-resilient equilibrium says no coalition of size K can gain by deviating. Now, historically, game theory did not consider K-resilient equilibria. It's not completely true. Bob Aumann, who won a Nobel Prize in game theory, did back in the 50s talk about strong equilibrium that was K-resilient for all K, but they basically didn't look at it after that. And I think sociologically, part of the reason is Nash showed that a Nash equilibrium always exists. You may have to randomize, but there's always a Nash equilibrium. That was his thesis, and he got a Nobel Prize for it many years later. Even two resilient equilibrium, that doesn't necessarily exist. That is, there are games where there are no two resilient equilibria, but there's always a Nash equilibrium. And game theory likes solution concepts that are guaranteed to exist for all games, I think, as a sociological matter. Now, what am I doing here? So, I want to talk about implementing mediators. That's the third thread. So, the Byzantine agreement, just before I leave mediators again, can be solved easily with a mediator if n is greater than 2t. Right, if you had a mediator, you could do Byzantine agreement, all agree on the same value. Each player tells the mediator his preference, and the mediator just chooses the majority preference. And you've solved Byzantine agreement with a mediator. So the question, and here's where I want to bring together game theory and distributed computing. Implementing mediators is a paradigmatic problem in game theory. And this goes back to mid to late 80s. And this was not obscure game theorists. Roger Myerson, for example, won a Nobel Prize. So this is a topic that was studied by quite well-known game theorists, just as multi-party computation. Remember back here, multi-party computation was studied by quite well-known computer scientists. If you look at Yao, Goldreich, Macaulay, and Vigdorson, we got 3 Turing Award winners there. That's our Nobel Prize. So these were problems that go back to the 80s, that were studied by leading people in the fields, and they're essentially the same problem. So when we implement a mediator, what game theory cares about is, suppose you could get a Nash equilibrium in a game where you had a mediator. Think of the mediator as non-strategic. The mediator announces their strategy. The players just play and maybe talk to the mediator. And you get a Nash equilibrium. Remember, Nash equilibrium means nobody can gain by deviating. Suppose you could do it with a mediator. And the question that the game theorists asked, can you do the same thing without a mediator? Can you decentralize the protocol? And they proved that the answer was yes, if you had enough players. But let me, before I get to that, let me claim that this is almost identical to multi-party computation. That, again, a multi-party computation, you had a problem you wanted to solve that you could solve with a mediator. And the question is, can you solve the same problem without a mediator? Now, they weren't, the multi-party computation folks weren't particularly looking at games. But if you stand back a few yards or a few meters, depending on where you're from, they're looking at exactly the same problem. How can you solve a problem? If you can do it with a mediator, can you do it without? And what I want to argue is that results that were proved in the late 80s in computer science subsumed the results that were proved in the late 80s in economics. But the two fields weren't aware of the existence of these results. They went along in blithe ignorance for almost 30 years until my co-authors and I came along and we generalized the results. So let me explain. So you can think of a Nash equilibrium as a one resilient equilibrium, right? You can tolerate deviations by one player. K-resilient equilibria, as I said, don't exist. But before I go on and leave the topic of fault tolerance, so remember, K-resilience means you can tolerate deviations by coalitions of size K. But that's not all the resilience I claim you need in a system like blockchain. So I want to be able to deal, let me call them irrational players. These are players that don't respond to incentives. Maybe because their utilities aren't what you thought they were, right? When the terrorists flew into the 9/11 and they flew into the World Trade Center, what were their utility functions? Certainly not placing a high utility on I want to live, which most people do. So maybe they're irrational. If you want to think in terms of computer science, maybe they have faulty computers. But apparently irrational behavior is not that uncommon, right? So if you look at sites like Pirate Bay and BitTorrent, people share files all the time. Why would they do that rationally? There's a small chance that they might get charged. I mean, you know, sometimes companies come after you if you post stuff in Pirate Bay. So you could argue it's not rational to do that. But people do it nonetheless. Maybe they like the feeling that I'm the one supplying everybody with their movies. So we might want protocols that can tolerate, both coalitions and let me call them irrational players, but they might not be irrational. They might be perfectly rational. You just don't understand their utility function. So to distinguish the two, well, let's start with a group of n bargaining agents. If they all stay in bargain, they get 2. But think of n as large. 100, 200. If they all stay in bargain, they get 2. Anybody who goes home gets 1. If anybody who stays, if not everybody stays, if they're not in case 1, if everybody stays, they get 2. But if some people go home, the people who stay get 0. So are we together? If everybody stays, everybody gets 2. And that's the best possible payoff. If some people go home, then the people who go home get 1, and the people who stay get 0. So I claim this game has 2 Nash equilibria. All right, audience participation time. What are the 2 Nash equilibria? All stay and all leave, exactly. If everybody stays, everybody gets 2, that's clearly a Nash equilibrium. Everybody goes home, that's also a Nash equilibrium. Because if everybody's gone home, nobody wants to deviate and stay because they get 0. Now you might say, well, it seems sort of crazy that everybody should go home. They get 2 if they stay. But imagine we're talking about a large group and everybody's acting independently. Is it really crazy to go home? Are you going to count on all these hundreds of people staying? I mean, you know, if you had a group of 2 or 3, maybe. But if you had a group of several hundred, you might just want to play it safe and go home, where you're guaranteed 1. Whereas if you stay, maybe one person, you know, they have a sick kid at home, so they go home. And you get 0 because one person went home. So people certainly take such possibilities into account. So my point is that everybody staying is a K-resilient equilibrium for all K, but it's not immune to deviations by even one irrational player. So again, we have 2 notions. We have K-resiliency, which is being able to tolerate deviations by coalitions of size K. And we have immunity, which is being able to tolerate T arbitrary players who are not necessarily rational. Okay, so the equilibrium where everybody stays is K-resilient for all K, but is not even one immune. If everybody goes home, that's K-resilient for all K, and is also immune for all T, T immune for all T. If I go home, I don't care what anybody else does. I'm going to get my one. Does that make sense? All right. So the question we're going to ask, which is where we're going to combine game theory and distributed computing, a KT robust protocol tolerates coalitions of size K and is T immune. I won't write down the formal definition. But again, the Nash equilibrium is 1-0 robust because it tolerates coalitions of size 1 and is not immune at all. Byzantine agreement is basically T immunity. It tolerates deviations by T, not necessarily rational players. So if you like, this is combining ideas of Byzantine agreement with the immunity and ideas from game theory of Nash equilibrium. So we're interested in KT robust equilibria that tolerate coalitions of size K and also tolerate up to T arbitrarily irrational players. What can we say? Sorry? Question? Sure. Sorry, what's the?
Mediator. My question is, what is the mediator in game theory?
So in game theory, they had, if you like, a cottage industry in game theory that still goes on of what's called implementing mediators. So technically, they imagined there were 3 games. There was an underlying what's called normal form game where everybody plays and gets a payoff. Then there's a game with a mediator where the mediator is a non-strategic player, doesn't get a payoff. The players can communicate with the mediator, but ultimately they perform the action that they perform in the underlying game, and their payoffs are the same as in the underlying game, which was a normal form game. And the question was, can the mediator help? And typically the answer is yes. For example, if you know some game theory and you know about correlated equilibrium, a correlated equilibrium is just like playing with a mediator who just sends messages and you don't talk to him, but you can have more general mediators. And then the question they ask is, if we can do something with a mediator, can we do it without the mediator? And they call that implementing a mediator. Any other questions? Do feel free to ask. All right. So let me let me state a bunch of results. I'm stating them not just to prove, gee, I can prove theorems, which I can, but that's not the point. Because you'll see the results and the assumptions we make are ones that are standard in both game theory and distributed computing. It also turns out that our results not only subsume results in game theory and distributed computing from before, but point out bugs and papers in major game theory journals. So actually major economics journals. So let me explain. So the first result says, look, if you have a KT robust protocol, that means it can tolerate coalitions of size up to K, and it can tolerate up to T arbitrarily irrational players. If you can do it with a mediator, then you can do it without a mediator. You can decentralize, get rid of the mediator, using what economists call cheap talk, which is just players talking to each other. But you can do it only if n is the total number of players, is greater than 3 times K plus T. So this is a lot like the Byzantine agreement result, where you can do it if n is greater than 3t. And indeed, some of our proof techniques use ideas from Byzantine agreement. And you can do it even if you don't know players' utilities. So the protocol is like a black box. Each player plays. They have utilities, but I don't have to tell you what it is. And moreover, and this is important, the protocol runs in bounded time. What I mean by that is after 17 steps, it's done. Some number of steps, fixed number of steps. It runs for that number of steps, then it's done. Now again, why should you care in this, decentralization conference? Well, you might find it much easier to design a protocol. You want fault tolerance. It's much easier to design a protocol imagining you have a mediator, imagining you have a trusted third party. Once you've got the protocol, you say, okay, but in real life, I don't have this trusted third party. Okay, you can get rid of the trusted third party. Players can just talk to each other. It's going to be complicated. It uses cryptography and all sorts of stuff, but there's like a compiler that will take your protocol with a mediator, compile it into a protocol without a mediator, but it only works if the total number of players is greater than 3 times k plus t. And that's a sharp bound. There's a matching lower bound. By that I mean there exist games with a mediator where you can implement it with a mediator, but you can't get rid of the mediator if n is less than or equal to 3k plus t. Is there any questions about that? So that's one result. And again, it sort of says, when can you decentralize? Now, economists talk about what's called a punishment strategy. That says, okay, you can cheat, you can try to lie and cheat and steal, but if I catch you, I can punish you. Punishment means I can use a strategy that gives you a worse payoff than you would have had if you hadn't cheated. Now, punishment is useless against the T irrational players. They're assumed not to be bound by utilities. But punishment can be very useful for the rational players. It says, okay, a rational player is going to worry about getting punished. We can show that now, if you have a protocol that works with a mediator, you can get rid of the mediator, decentralize, if 2k plus 3t is less than n. So before it was 3k plus 3t, so you've saved the k. Remember, k is the number of rational agents. They're forming a coalition. So if 2k plus 3t is less than n, then you can implement a mediator. But unlike the first protocol that's bounded, that runs in like 17 steps, the second protocol, the 2k plus 3t one, is randomized. And it has to be randomized. Randomized says you're tossing coins basically to decide whether or not it's time to stop. And it has a finite expected running time that's pretty low, but it's not bounded. It could take arbitrarily many steps, although the more steps, the probability of taking 20 steps is basically exponential in 20. The probability of taking n steps goes down exponentially with n, but it's not 0. So keep that in mind when I talk about results that were wrong in major game theory, major economics journals. Now, sometimes, not typically in blockchain, but in other distributed computing applications, you assume that there's a broadcast channel. That's sort of like you don't have to do business agreement because you get a broadcast channel for free. So in that case, you can implement a mediator if 2k plus 2t is less than n. But there's a small chance that your protocol might fail. You can get it down, that epsilon down, as small as you want, but you can't make it 0. And if we assume that one-way functions exist, which is a standard assumption in cryptography that says there's a function that's easy to compute but hard to invert. That's what one-way function means. And there's a punishment strategy, as in part B. Then you can implement a mediator as long as n is greater than k plus t. And again, there's a small epsilon error. Now the point is, why do I prove all these results? These are the kinds of assumptions that people make in real-world systems. And they're willing to tolerate epsilon error. So this tells you really when you can decentralize. And the next result tells you, and that's the best you can do. So I should say, before I go on, if I have time at the end, I'll actually give you the idea of the proof. But the proof uses secret sharing and multi-party computation ideas. So Byzantine agreement, multi-party computation, and game theory, they're all coming together here. And then I have matching lower bounds. Basically says all the results are tight. By that I mean there exists something you can do with a mediator that can't be implemented without a mediator if 3k plus t is greater than n. If 2k plus 3t is greater than n, there exists something you can do with a mediator that can't be simulated without a mediator, even if there's a punishment strategy, and so on. I mean, so basically, all the results on the previous slide are tight. They're the best you can do. Let me stop and ask if there's any questions. Yeah, probably helps to have the mic.
I'm not sure if the question is in context, but if, I mean, you have the rules that bound what you can do, but in practice, you cannot be sure to have Sybil resilience, right? So that makes
it
kind of theoretical, because you don't know how many individual actors will build your set of n. You don't really know n, right?
In blockchain, so these results make more sense in distributed systems where you know the number of actors. In blockchain, an open system, you don't. So this would make sense, and even worse, these results assume that the set of agents is constant, stays the same over time. And in blockchain, you know, it's an open system, you have people entering and leaving the system. So this would make sense in a company blockchain where you're implementing it inside the company and you have control over the agents. And it's actually a really interesting open question. What happens, what can you do in an open system? And I don't know the answer, I have no clue. But it's a good question, and as you see, I don't know the answer. Did I understand the question correctly? That's what you intended?
Yeah, I guess so, yeah. Thank you.
I saw another hand over there, so. But I think something might be doable. I should say that I don't think it's lost cause, but these results definitely assume that the set of agents is known. But now you've got me thinking about it. It might be enough just to know that there's a minimum number of agents, which you might know even in an open system. So it's actually a really interesting question. Sorry, go ahead. Sorry, was there another question? All right, if not, I'll keep going. But again, do feel free to interrupt. So let me mention lower bounds and running time. So if you're in the situation, well, I mean, if 2k plus 3t is greater than or equal to n, then there's a game with a mediator that can't be implemented deterministically. You actually need to randomize. So I had algorithms that use randomization. It's actually necessary. And why am I mentioning this? Well, stay tuned. And in fact, for all B, you can find games that require more than time B in expectation to implement. So, and there's a game that we can't implement with a mediator that runs in less than B steps. So why do I care? Well, let me talk about related work. So there's lots of related work and implementation in both computer science and game theory. In game theory and economics, the work of François Forge and Barani, which dates back to about 1990, it proved that you could implement a mediator with 4 players. Now, they were looking at Nash equilibrium, so that's a special case of the result. You can do it as long as 3 times k plus t is less than n. Well, take k to be 1 and t to be 0, and you have the game theory result, and you can implement it with 4 players. So, but it turns out that the work their work, which was 1990 and, you know, pretty well known in game theory, turns out to be subsumed by work that was done, well, that's not completely fair. There's work by Ben Orr, Goldreich, and Vigdorson in computer science, a very famous paper, and Shom, Crepeau, and Damgard, both came out in '88. They showed you could do multi-party computation and for all k and t, and actually theorem 1a, the general version, with a bit of work, follows from that result. So game theorists proved it for k equals 1. Computer scientists proved it for all k and t. Well, you had to work at it a bit, but the ideas were already there. Ben Porat proved theorem 1b, that's the 2k plus 3t result. Let me just go back to remind you. So Ben Porat proved part B here, but his proof was buggy. It was published in JET, Journal of Economic Theory, a well-known econ journal, and how do I know it's buggy? Well, his algorithm is bounded. You just look at the algorithm. You don't have to know anything at all about economics. Just look at how he describes the algorithm, and you can see it takes something like 8 rounds. It's bounded. Our theorem says if you have 2k plus 3t, and in particular if k is 1, there is no bounded algorithm. You have to randomize. So we knew that there was a bug in his algorithm. It took us a couple of days to find the bug, but we knew it had to be buggy because his algorithm was bounded and we knew there was no bounded algorithm. He published sort of a, he agrees, by the way, that it was buggy. Heller extended Ben Porat's result to all k and proved a matching lower bound. His version wasn't buggy, although it did have problems. So in the computer science literature, Lisenskaya and Triandopoulos proved theorem 1c for k equals 1. So remember, 1c is the one that says if you have a broadcast channel, we'll get there. If you have a broadcast channel, then you can implement the mediator if n is greater than 2k plus 2t. So we all had, you know, people had special cases of our results. In the econ literature, Urbano Villa and Doris, well, they're econ, and Doris Halevi and Tal Rabin, computer scientists, they proved theorem 1d if k equals 1 and n equals 2. But unfortunately, the Urbano Villa algorithm is bounded. Again, it took us a while to find the bug, but we knew it had to be buggy because it was a bounded algorithm, and we know there's no bounded algorithm. And yes, they agreed that it was buggy. So it's amazing. People get fooled by these results. Okay. That work is already over 10 years old. More recently, we've been looking at asynchronous systems. Now think of blockchain as a partially synchronous system. There is still a bound on message delivery time. But when I say asynchronous systems, I mean there's no bound on message delivery time, and messages, it could be infinite, so messages might get lost. And it turns out, so all the results that I've proved so far are for synchronous systems. It turns out if you have asynchronous systems, arguably markets are asynchronous, and blockchain is certainly, you know, partially synchronous. You get the same results, but you have to pay a bit. So instead of 3k plus 3t, you get 4k plus 4t. But there's also technical issues about what it even means to implement a mediator in an asynchronous system. The real issue is that typically in asynchronous systems, it's assumed that there's a scheduler that says, okay, you're going next. Now let's wait for 3 rounds. You can go next. We'll wait for 5 more rounds and you can go. So the scheduler decides who goes when and how long the gaps are. And the scheduler also decides how long it takes messages to arrive. So it turns out that the outcome of an algorithm might depend on a scheduler. And we want to say that the algorithm, if it works no matter what the scheduler is. And so we want it to be the case that for each scheduler in the mediator game, when you're implementing the game, there's a scheduler that implements the same outcome in the communication game where you've decentralized and players just talk to each other, and vice versa. And again, we get sort of similar results, but everything gets bumped up by 1. So instead of 3 times k plus t, we get 4 times k plus t. And instead of 2k plus 3t, we get 3k plus 4t if there's a punishment strategy. And they're matching lower bounds. So the point I wanted to make in this talk is that if you're thinking about blockchain or issues of coalitions and fault tolerance are critical in distributed computing and game theory and cryptography. Again, historically, game theory did not think about coalitions and fault tolerance, but I think they should, and I've been trying to convince them. Distributed computing and cryptography historically did not think about rational players. Now they do. And by combining ideas from these 3 areas, we can prove interesting results, and I think useful results. And let me stop and ask if there's any questions. But if there aren't, I'm going to give you a sense of how the proofs go, because that takes into account, at a very high level, that takes into account multi-party computation. Any questions? Yeah. They never considered fault tolerance. So to me, what it means is getting notions of equilibrium that allow for deviations by larger coalitions and arbitrary irrational players. So if you're saying, how do game theorists define it? They didn't. They didn't think about it. So I think our definitions, you should, at least in my opinion, you should view them as how to define fault tolerance for games. Any other questions? All right. So if you were a bunch of economists, and I have given this talk to economists, most recently, Roger Myerson is somebody I know moderately well, and so I gave the talk at the University of Chicago, and I had, it was just the game theory group and econ group, and basically, so here's the message I want to give them, that equilibrium notions should be more robust. They should take fault tolerance into account. Cryptographic techniques can be helpful in achieving equilibrium. I'll show you that in a second. And other ideas from distributed computing may be relevant. Think about, I haven't worried here about computational limitations. What happens if I do? Why does economics never take asynchrony into account? It's standard in distributed computing. So let me give you the idea of the protocol. This is the 3K plus 3T, and it uses what's called verifiable secret sharing and circuit computation. So how many people here have not heard of verifiable secret sharing? You've all heard of verifiable secret sharing? I mean, raise your hands if you haven't. Great audience. So again, just to remind you that with verifiable secret sharing, each agent has a share of a secret. And typically, this is the version due to Adi Shamil, you have a polynomial. If you want to share the secret among m-1 players, you take a polynomial of degree m, take the secret to be f of 0, f is the polynomial, and give each of the players, you get f of 1, you get f of 2, you get f of 3, f of 4, so each one of them gets a point on the polynomial. Any m+1 agents can put together their shares and reconstruct the secret. So if I have m+1 points on an m-degree polynomial, I can reconstruct it. But if I have only m points, I can't. I have no clue what the secret is. So remember that. You all said you knew it. So here's the idea for how we do the 3k plus 3t. We imagine we want to compute what the mediator does. We want to get rid of the mediator and implement the mediator. Imagine, and this is without any real loss of generality, that we can implement the mediator as a circuit. What I mean by that is a circuit with AND gates and OR gates and plus and multiplication. It's the plus and multiplication that really matter. So at the top of the circuit, that x1, x2, x3, and so on, they're the inputs of the n players. Each one has their own input. And you want to compute some function of that. So how do you implement the mediator? You assume that each player has a share of, so we all share with each other what we're telling the mediator. And the mediator we're assuming is a circuit. It does its computation. And the idea is at each, we can do what's called circuit computation. Each one of us, so we all have a share of the initial values. And then at every step, we can arrange it so that we each have a share of that node. So does this have, no, it's, so if you look at that circuit, I want to arrange it so at the beginning, if I'm player 1, I have a share of x1, x2, x3 up to xn, a share in the sense of secret sharing. And then at the next step, I'm going to have a share in the values at each of the nodes below that. And at the next step, I'm going to have a share in each of the nodes below that. And after whatever the depth of the circuit is, I'm going to have a share in what the mediator said to do. Right? So I'm implementing the mediator. So at no point do I know what the mediator says to do. I just have a share. And at the end, each one of us has a share on what the mediator says to do. Then we all share our shares. And as long as there aren't too many faulty guys, we can reconstruct what the mediator would have said. So we can implement the mediator. At no point do we know what's going on, up until the very end, where we can share our shares and we'll know what the mediator would have told us to do. And so we've basically implemented the mediator without revealing any other information using these ideas of multi-party cryptography, multi-party computation. So the key point is that you can use circuit computation and secret sharing to reconstruct the mediator's protocol in such a way that you don't reveal anything. And that's all I have to say, but I'm more than happy to answer questions. Questions going once? As in verifiable secret sharing?
Yeah. Why verifiable secret sharing is verifiable? Yeah, what is verifiable about it?
At the end, so I didn't name it, it's not due to me, but at the end, each person can check, we've reconstructed a polynomial, so we'll know we'll know everybody's share, and we can reconstruct the polynomial, so we can check that nobody's lying about what they did, because at the end, when we're computing, in this case, the final answer, we can check that we really have the final answer, because we can confirm that the polynomial is the right polynomial. But actually, let me say more about that. There is this question, sort of mysterious, where does the 3 come from? Why do you need n greater than 3t? And I can give you an answer to that that sort of relates to your question. It's not a proof but it's an intuition. So imagine you have t equals 1. You just want to reconstruct your polynomial as a line, right? So with 1 point on a line, you can't reconstruct the line. If I tell you 1 point, you have no idea what the line is. With 2 points on a line, you can reconstruct the line. But if you have a faulty agent, you're in trouble, because suppose you want to tolerate one faulty agent. It's true that with 2 points you can reconstruct the line, but if you have a faulty agent and they lie, then you're in trouble, because you don't know what the right, I'll tell you this point, somebody else says this point, and the faulty agent says this point. Well, which line is it that we want? But once you have 4 agents that, even with a liar, you can, with 4 agents, if each one of them tells you their point in the line, it's true that one person might lie, but 3 points have to be collinear. So you'll be able to identify the faulty agent, and you'll know the line. And you'll be able to verify that it's the right line. And that generalizes. If you have up to k faulty agents, but you have if n is greater than 3k plus 1, you can even if the agents lie about their point on the polynomial, you can reconstruct the polynomial, and you know the correct polynomial, and you know who the k agents are, you know who lied. But with less than 3k plus 1, that's not true. So again, it's easiest to think about a line where if you have 4 agents, one of whom might be a liar, and you want to do verifiable secret sharing with k equals 1, then everybody tells you their point in the line, and even if one person lies, you can figure out what the line is, right? Because you're going to have 3 collinear points. And that generalized, so if you had 7 agents, now it's a parabola, not a line. But if you have 7 agents and up to 2 lie, you can still figure out what the parabola was and who's lying, and so on. So in general, with 3k plus 1 agents, you can do verifiable secret sharing, but moreover, you can tolerate k faults in the sense that even if k people lie about their values, you can figure out who they are and get the right answer. More questions?
The irrational player, they might play irrationally in the game, by simulating the mediator, they act rationally,
Okay, so here it's assumed that we have point-to-point communication. So when you send a message to a mediator, you know you're sending it to the mediator, not to. So sure, the irrational player can pretend to be the mediator, but again, it's point-to-point. So we assume that you know you're sending it to. So it can use the mediator's protocol, but it can't pretend to be the mediator in the sense of getting the mediator's messages. And it can't spoof the mediator in the sense of saying, well, I'm the mediator, here's what to do. But that's an assumption that's built in, and I can certainly imagine you might want to weaken the assumptions and see what you can do. More questions?
I have a question about this circuit. So when you have these shares, is it my understanding correct that you know that you compute the final thing in the end because of polynomial algebra, because the shares are evaluations of polynomials of some points, and then in the end you know that the evaluation of the final polynomial at 0 would be like the combination of evaluations at different other points?
Essentially, yes. So it doesn't have to be binary. It doesn't have to be 0, 1. So the theorem allows the nodes can be additional multiplication gates, so you can get natural numbers. It's assumed that the circuit is known, so you're sort of computing it step by step. But I think otherwise what you said was correct.
So my question would be also how much of a restrictive computation model is arithmetic circuit, whether you basically can do everything in it, or there are some things...
You can do everything that you need to do for this proof. So can you do everything? You can do a lot with arithmetic circuits, but the point is you can represent the mediators in an arithmetic circuit. And that's all I need for this argument, because I'm trying to implement the mediator. It's hard for me to say that you can do everything because I'm not sure what everything is. More questions?
Communication become asynchronous.
The factor of 4 when k is 1.
Because here you say I have to have 3k plus 3t. No, that's
So I was just assuming t was 0 when I said 4.
oh, okay.
But no, of course, in general, you need more than 3k plus 3t.
But even in that, so we have no faulty agent, but we have...
Yeah, you can tolerate arbitrary, rational, and faulty agents as long as n is greater than 3 times k plus t.
And then if your communication become asynchronous, that become 4, no? That is what...
Sorry?
And when your communication become asynchronous...
Oh,
then
asynchrony things get more complicated.
Okay.
Let me punt on that. We don't do this, we do something else, and it's more complicated. I can certainly point you to the paper. I can't reproduce it off the top of my head now. And we also prove it's a tight bound. So you're not going to do better. So it's a good question where here I feel like I sort of explain where the 3 comes from, but with asynchrony, the extra 1 seems to come from needing to deal with the scheduler, but I don't have a clean way of making that precise. More questions? Okay, we're done.